All right, this is the Geometry Chapter 10 final review for Semester 2. So Chapter 10 was all about the areas of different shapes, and then we talked about the probability, geometric probability using the area of different shapes eventually. So we started with talking about finding the area of parallelograms and triangles. What I'd like to do at the top of the page, I'd like you to write those area formulas with me. So for a parallelogram, it's actually the same as it is for a rectangle. It's base times height. But the key is that the base and the height have to make a right angle. Triangle formula, hopefully you know that one right now. There's three parts to it. It's 1/2 base times height. And so these are the formulas we're going to use on this page. This is find the area of the parallelogram below. So this first one, we know we're going to be using our parallelogram formula, base times height. And like I said, the base and the height have to make a right angle. So what I do is I look for the right angle, and I see that's the 10 and the 8. So I just go 10 times 8, and I get 80. Now, area should always have a unit to go with it. So if you look, the unit they're using is inches, and area is a squared measurement. It's two-dimensional, so we square it. All right, you pause the video and try the next one on your own. All right, you can see that I had my base and my height. I followed that right angle that was kind of on the left side. I looked at the two sides that make that up. That's a 12, and then this side doesn't have a measurement here, but opposite sides on a rectangle are parallelogram are congruent, so I can bring that 8 over. 8 times 12 then is 96. I gave it the label millimeters squared. So we like to do stuff with composite figures too, like this one. It says a scale drawing of the side view of a house is shown at the right. Find the total area of the side of the house in the drawing. So we just want to split this up. I see two different shapes. I see a rectangle, which is base times height. That's pretty easy. And then I see a triangle, which is our 1/2 base times height. So the key that you know the height of that triangle right now is 8, but you need to know the base. Now, since we do have a rectangle below, we can actually bring that 20 up. And we get 20 for the base of that triangle. So let's do the triangle first. It's 1/2. The base is 20. The height is 8. I go 1/2 20 times 8, and we get 80. Then we do the rectangle. The rectangle is just base times height. We go 20 times 24. Multiply that out, we get 480. Now, in order to get the entire shape, you have to actually add those two numbers together, and you get 560. Now, we do need to have a label with this. They're using feet, so we're going to go feet squared. We move on to triangles next. It says find the area of the triangle. Now, this is a regular triangle. We have 3 sides, but what we don't have is the height. So you can kind of draw that in, the height right here. Since this is a regular triangle, all the sides are the same. This height that is what we call an altitude. It cuts the base in half. So you get 4 and 4. Why that might be useful is in order to do the 1/2 base times height formula, you need the base and the height. Well, right now I've got the base is 8, but I don't know how tall it is. It's not 8 units long, it's 8 units tall. It's going to be shorter than that. So what I can do is call this height maybe x, and then if you look, you have a right triangle, and you can use a right triangle, the Pythagorean theorem, to get that height. So we can go x squared plus 4 squared equals 8 squared and work backwards from there. Now, if you remember your special right triangles, you might also be able to get this a different way. I'm just solving this. I bring that 16 over to the 64. I get 48. And x then equals the square root of 48, which is 6.928. And then what I can do now is go take that, plug it in for the height here. Whoops. And I can get the actual area of my triangle. If you remember your special right triangles, you had a 30, 60, 90 with the height being 4√3. I multiply all my numbers and I get an area of 27.712 feet squared. Now on your homework and on your final, it will tell you exactly what to round to, and so you can be a little more accurate with your rounding there. After that in the chapter, we moved on to finding the area of trapezoid, rhombi, and kites. So a trapezoid, we had a little song to go with that. We said first base 1, second base 2, add them together, because that's what you do. Multiply the height, divide by 2, that's the area of a trapezoid, and we ended with Yahoo! So that's our trapezoid. Rhombus is 1/2 d1 times d2. And kite is actually the same thing as well. 1/2 d1 d2. So it's just knowing what your pieces are and being able to plug them in. Why don't you make sure you're leaving your answers in simplest radical form? It does say that. Why don't you pause the video and try to do as many of these as you can using those two formulas up above. Alright, so I got the first one. I just had to plug in my values. My bases were 16 and 9, and my height was 10, so I went 16 plus 9. That got me 25 times 10 is 250, divided that by 2 and got 125 feet squared. I skipped this trapezoid for now and went down to the kite and the rhombus, or actually these are both kites. 1/2 d1 d2, don't forget when you get those diagonals it's the entire length, so I had to go 8, 4 plus 4 is 8, right here. And then 2 plus 6.5 is 8.5. Went 1/2 times 8 times 8.5 and got 34 feet squared. Similar thing over here on the next one, that diagonal is 12. This diagonal is 15. I went 1/2 15 times 12 and got 90. So let's go back to this one up here. It says, find the area, leave your answer in simplest radical form. If we're looking at this one, you can see it's a trapezoid. You need base 1 plus base 2 times height divided by 2. So right now I have base 1 is 14 plus an unknown base 2 divided by 2 and an unknown height. So I have to figure out two things, the height and second base. So I can maybe put in this line right here, that would be the height. And if you look at that, that kind of splits the shape up then into a rectangle over here on the right and a triangle over here on the left. That leaves us with a few choices then. Since it is a triangle here on the left, you can, and you do have an angle, you can use trig or you can use your special right triangles to find out that height. I would probably use my special right triangles. I see I have a 30, a 90, and then a 60-degree angle. If I'm using my 30, 60, 90, that's 1 square root 3, 2. My 10 is the biggest. Across from the 30 would be my smallest. That's my height. So I go backwards and I get, oh, that height is 5. And I can figure that one out right there. The trick on this one then is, well, you've got your height, you can plug that in, but you need your second base. So your second base is going to be 14 minus this side length. And so you need to actually find that side length using your ratio. Come get the middle one. It's just going to be 5 times the square root of 3. You get 5 root 3. So then that second base is 14 minus that 5 root 3. Which is kind of not a super fun number to deal with, but we can deal with that. Plug it in. You do have a calculator at this point, so when you type this all in, parentheses are super important. I'd go 14 plus 14 minus 5 square root 3. You can type in that square root 3 in your calculator. Scroll out of the square root, close your parentheses, multiply by 5, and divide by 2. And you're going to get a decimal. Or actually, it says to leave your answer in simplest radical form. If we got a decimal, you get 48.35. But if I'm going to leave this in simplest radical form, I combine all the terms I can. I go 14 plus 14 is 28. I'd get left with 28 minus 5 root 3 times 5 divided by 2. Personally, I just wouldn't leave this one in simplest radical form. Let's leave it as a decimal, give it a label, centimeters squared. And call that good enough. All right, let's go look at the next one. It says, given the regular polygon, find the measure of each numbered angle. So we started with these regular polygons with a few different formulas. We said that it's actually easiest to get this angle 1 here. We call that a central angle. Because if you look around this is a pentagon. It's got 1, 2, 3, 4, 5 sides. There's 5 central angles then. So to get that central angle, we go 360 divided by 5. And that gets us 72. So that gets us angle 1. So the measure of angle 1 equals 72. But we need 2 and 3 as well. So we go look at maybe angle 2. Angle 2 is right here. It's part of what was a central angle, but you can see it actually takes that central angle and it kind of cuts it in half. Well, it doesn't just kind of cut it in half, it actually does cut it in half. So we just take that 72 of the central, divided by 2, and we get 36. And now we need to go get that angle 3. That's down here. You can kind of see that there's a triangle formed right there. Well, at this point in the year, I hope you know what all the angles in a triangle add up to. 180. So we can subtract off that 36 degrees, which was angle 2, and this little 90-degree angle right here, and we can get angle 3. And we should end up with 54 degrees. All right. So that's kind of going through finding the measure of each numbered angle. When we started to use that was down here when we started talking about regular polygons areas. This one gives you the apothem and the side length, and we're rounding our answer to the nearest tenth. We had a formula for the area of a regular polygon. I want you to write this down. A equals 1/2 apothem times side length times number of sides. Now there's two separate problems here, splits right there. This first one, they give us everything, so we're just plugging it in. I'm going 1/2 apothem, that's A, 4.9. Side length, that's 7.1. And then they actually gave me the number of sides by telling me it's a pentagon. Penta means 5, it has 5 sides, I plug in a 5. And I just go type that into my calculator. I'm going to go 0.5 times 4, or 1/2 times 4.9 times 7.1 times 5, and I get my total area to be 86.975. It does say to round your answer to the nearest tenth, so that rounds to 87.0. Give it a label, inches, its area, square that label. So that was just in general using our formula. We were able to kind of derive, to find pieces when we were given specific regular polygons, like a hexagon. Because what we were able to do was use trig or our special right triangles to find these different things we need. Because you need A, you need S, and you need N. We can see they gave us 12. That's your side length, S, and it's how many sides there are. You go around 1, 2, 3, 4, 5, 6. There's 6 sides. So the last thing we need is an apothem. The way to get that is you put a center dot in the middle of your polygon, and then you draw out 2 radii. A radii goes from the center to a corner. Okay, so those are your 2 radii, and then you draw in an apothem. That goes from the center to the middle of a side. Now, we have that one of these side lengths is 12, but half of this side length is 6 and 6. And so what we can actually do is we can find the measure of a central angle to get us one angle right here, and then use our special right or our trig depending on the angle measures. So if there's 6 sides, to find the angle measure, I go 360, cut it into 6, and I get 60 degrees. And then I want to cut that in half because this makes me a little right triangle, and I get 30 degrees. So that sounds like a 30, 60, 90 triangle to me, which gives me the ratio 1 square root 3, 2. I go, well, right now I have the 6, that's across from the 30-degree angles, so that's the smallest. What I need right now is this apothem, this red line. You can see that that's across from this angle right here. Well, if you've already have a 30 and 90, this one must be 60 degrees. So it's going to be your middle number, so you just multiply. You get 6 root 3. That's my apothem then, and now I'm just ready to go plug everything into my formula. 1/2 apothem, side length, number of sides. Round my answer to the nearest tenth. I've got something like 374.1229. That becomes 374.1 inches squared. I hope some of this stuff is coming back to you now. We're making our way through this packet. We've got a little bit left to go still. After that, we talked about being able to find the perimeter and areas of similar polygons. So since the figures are similar, give the ratio of the perimeters and the ratio of the areas of the first to the second. So this is where we talked about A to B and A squared, B squared. This is your scale factor, AB, or your perimeter ratio. This is your area ratio, a squared, b squared. And so those are what we want. In order to figure out your perimeter scale factor, your perimeter ratio, your scale factor, we take a side length to a side length. So once we go from the first to the second figure, so I go 8 to 6. And we just simplify if possible. You can take a 2 out of both of those, and you get 4/3. That's your perimeter ratio, 4/3. But now you want your area ratio. So if you look to go from AB here to a squared, b squared, you square it. So I go, oh, 4 squared is 16, 3 squared is 9. I've got my perimeter ratio and my area ratio. You pause the video and try the next one. All right, I got my perimeter ratio to be 2/3 when I simplified 14 to 21, and my area ratio to be 4/9. So once we have these different types of ratios, what we can do is we can actually find areas or perimeters when we know one of the shape's actual areas or perimeters. So we start with our ratio usually. So it gave me a side of 6 and a side of 15. It says the figures are similar. The area of one is given, so area of the smaller is 60. I like to write that in the shape. Find the area of the other. It's the nearest whole number. So if you look at those 6 and 15 we talked about in the beginning, those are side lengths. That's perimeter. So what I'm going to start by doing is just maybe writing those as a ratio and simplifying it. I can take a 3 out of both of those and I get 2/5. This is my scale factor or perimeter ratio. But what I need to compare are their areas, because that's what I want, to find the area of the other. So I have to turn this scale factor into an area ratio. So I take 2/5 and I square it, 4/25. Now I'm actually ready to set a proportion. This 4/25 is going to be part of it. It goes from the smaller to the larger rhombus, because they're smaller to larger number. And I have the area of the smaller. So I put the smaller here. What I don't know is the larger there. And then after this point, I just cross multiply and I solve. I get 4x equals whatever 25 times 60 is. That's 1500. Then I just divide both sides by 4. I get 375. I do need to give it a label. It's an area. These are all in meters for the units, but it's area, so I square it. Okay. Once we had gotten good at those perimeter and area ratios, we moved on to talk about some other kind of weird shapes. So we moved on to talk a little bit about some different formulas. We were able to find the area of regular polygons and triangles using trigonometry. So we developed a new formula for the area of a triangle. That formula is called 1/2 BC sine of A. Now you might be asking, what are B, C, and A? B and C are two sides of the triangle, and A is the angle between them. So like in this first one, we have a side of 6 and a side of 4, and 68 is between them. That's perfect. I'm going to use 6 and 4 as my B and C, and 68 as my A. And I just plug it all in. 1/2 6 times 4 sine of 68. Now, this is where you might get something weird if your calculator's in the wrong mode. So mine's in the wrong mode right now, and I got 3.25. That means my calculator's in radian mode. So what you need to do is on the top left of your graphing calculator, there's a button that says mode. Click on it, go down to where it says radian, and scroll over to degree and hit enter. Now try this again. 0.5 times 6 times 4, sine of 28, and now it should be in degree mode, and you get, oh, the area of this triangle. Get the area of this triangle to be 11.1. I just realized that when I got that 3.25, I even had the wrong angle measure in. So let me see what you would have gotten in radian mode actually. You would have gotten negative 10.77, which is weird. Those aren't right. Those are in radian mode. Degree mode will get us the 11.1. Pause the video and try the next one on your own. You can see my work up there. My sides were 12 and 11. 33 degrees was the angle between them. Typed them all in. My calculator is in the right. It's not in the right mode. So my answer was if it was in radian. Sorry about that. Oh, I was in the wrong thing here. What we should end up with here is 35.9 inches squared. All right, we're getting there. Let's finish this slide. It says find the area of the regular polygon, round your answer to the nearest tenth. So the reason why we talked about this 1/2 BC sine of A stuff is we were able to use this to help us in order to find the height or the apothem right here in some of these weird shapes. So like this is our regular polygon. That's our formula 1/2 ASN. Where we need A, we need S, and we need N. If you look at this shape, it's got 1, 2, 3, 4, 5 sides. That tells you N is 5. What the picture does not tell you is the apothem or the side length. So those are two things we need to find. I like to call the apothem A, and this side length, not the whole thing, but half of it, X. And so what we're able to do if we can use trig then to find this little, and get this angle measure to find that apothem. Because we have that this radius, that's what we call this black line on here, is 6 feet. And so what we have to figure out what's the central angle. So we go 360 divided by 5. That gets us 72. That's the entire central angle made by 2 radii. What we've actually done is cut that in half though already. You can kind of see that now, and that's 36 degrees. Now we can use that 36 degrees in lieu of the trig to figure out the apothem and the side length. So I like to think about, okay, I have a 36 degree angle, so I'm going to use something with 36 degrees. And I have 6 as a side. If you look, that's across from the 90 degrees. That means it's a hypotenuse. And if I need the apothem, that's adjacent. Well, if I'm thinking SOHCAHTOA, that sounds a lot like cosine, adjacent and hypotenuse. So I go cosine of 36 equals the adjacent A over the hypotenuse 6, and we can solve that. Let's set up though to find that x2. Well, x is then opposite, and I have the hypotenuse 6, so that sounds like sine. I go sine 36 equals the opposite x over the hypotenuse 6. Now I can solve both of these to get x and my apothem. All right, I got my apothem to be 4.85. I'm going to give it a few decimal places more, 4.854. My side length, 6 sine of 36. I got that to be 3.527. Now I'm ready to plug everything into that 1/2 ASN. I go 1/2, 4.854, side length 3.527, 5 sides. That's what you might think. However, you have to be really careful because what we found right here in this sign, and I wrote it down for S, but it's actually not the side length. It's actually half. To get that entire side length, we need to take that 3.527 when we went 6 sine of 36. So we need to take what we get here for x, which is 3.527, and we actually need to remember to double that to get the entire side length. So take that and times it by 2, and we get something more like 7.054. That's our side length. And that's what we want to use on our formula. So try it again. We go 1/2 times 4.854 times 7.054 this time times 5, and we get that area to be 85.6, and I think our label was inches squared. Okay, it was a little bit weird and tedious, but we can use trig to help us out with that to figure out that area.